Good afternoon, everyone, and thank you for coming. My name is Shailesh Birari. I have been working with Netflix for over a year now. We have been working on Dynomite. Prior to joining Netflix, I was working for Clusterix, which is a distributed relational database startup. So today we'll be covering Dynomite, open source product that we have developed in-house. I'll be talking about Dynomite, its architecture, its topology, replication, and Yanni will then come in and talk about the rest of the components of Dynomite, which is Dynomite-manager and the Dyno client. So as you know, our most important, main primary business use case is to stream movies at no matter what. So for us, availability is very important. Right. So for that, we actually moved from a relational database like SQL or Oracle to Cassandra. But over time, Cassandra became a de facto data store for all our data. But since we were also microservices-based architecture, new services came up which required really high throughput and low latency kind of data store, and Cassandra could not really keep up. So what we really wanted was a new data store which would be very, very scalable, highly available. That's very important for us, and which would serve good throughput and low latency for the services that were demanding this load. A typical deployment in Netflix is basically we use three data regions, three data centers or regions, what we call it, and each region or data center has three availability zones. And the apps deploy in all the three regions, right, and all three availability zones. So essentially, the data store, what it means for a data store is it is going to get a read or a write from any of the availability zones. So what it essentially boils down to, the underlying data store should be active, and we should have a multi-datacenter replication. So that was primary design goals for our new Dynomite thing. Of course, Redis was gaining popularity. It had advanced data structure, so it provided much cleaner and better data modeling aspects. But what we really wanted was active, highly available multi-data center. I'm repeating this again and again, highly available, because that's how important it is for us, right? And so, and we did not have bidirectional replication with Redis for a master-slave kind of architecture. And to provide high availability, what we actually initially do, we internally do is we run Chaos Monkey kind of failure testing. If you do not know, you can just Google for Chaos Monkey Netflix. So they have like three types of failures. One is Monkey, where arbitrary node just gets killed. Another is a Gorilla, where an entire rack gets killed, and a Kong, where the entire region gets killed. So what we want is ultimately this data store that we are coming up should be available even after these monkeys are creating chaos in the data centers, right? So that's how we test our internal services. We want to make sure that it's available and the movies get streamed no matter what. So having said that, we came up with a new product called Dynomite. What it essentially does is it's basically a generic layer on top of non-distributed data stores like Redis, Memcache, LMDB, etc. The primary focus over here is performance. Again, cross data center, active replication, and it has to be highly available, right? We have two types of use cases for Dynomite internally. One is as a cache, and the other is as a data store. So for a cache, if a node goes down and you don't find the data, it's fine. You can just bring it up from the backend data store. But when you are using it as a data store for like temporary data and all, it is not significantly problematic, but it can be still not good to lose the data. So for that, we actually implemented some really good features in Dynomite. We implemented node warm-up. What it means that when a node goes down or it gets killed by AWS and a new node comes up, it is going to get its data from its peers. So essentially, it means that the client will not see the client for some time. It will fail over, and when then the node comes back, it is having the data again. Tunable consistency. So some of the applications we have require to read the data that they have written, right? So for them, we introduced two types of, we introduced the quorum kind of consistency. I'll be covering that in the subsequent slides. So that way you can actually read the data that you have written. And last week we introduced S3 backups and restores for kind of for the applications where you cannot afford to lose the data. You essentially have backups to S3, nightly backups to S3. So all these features were pretty recently introduced. So consistency we introduced in last August. Warm-up we did it in February, and S3 backups Ioannis just introduced in last week. So that's how rapidly we are developing Dynomite over here. The current status of Dynomite is it open source and fully integrated with the Netflix ecosystem. It lives on GitHub alongside the other Netflix projects. Having said that, it is rapidly developing. It is young. It is just maybe 2 years in development, but that doesn't mean that it is immature. It is fairly mature. It is stable. It has been running for 1.5 years in production. In fact, I am on-call primary for Dynomite right now. So that's how that's how stable it is. And we have around 1,000 customer-facing nodes. They take around 1 million ops at peak. The largest cluster deployment that we have around 6 terabytes of data. And so initially we were deploying very fast, but now we have started gradually reducing the deployment, and we do like quarterly upgrades along with hot fixes every now and then. So the project lives on GitHub. The master is the stable branch, and if you want to try it out, you should try the master branch. That's what we run production. So let's take a overview of what Dynomite looks like. So it's a layer on top of a non-distributed key value data stores, right? It can be used in multiple data stores, but all of our production deployments use Redis underneath. We have peer-to-peer shared nothing architecture. What it essentially means that all nodes in the Dynomite cluster are similar. There is no master or a slave or anything like that. There's no leader election or anything. Both architecture like master slave or peer-to-peer has their own pros and cons, and it depends on what are your use cases and what fits your needs, right? So for us, high availability was important. That's why we chose peer-to-peer architecture. It does auto sharding, so it uses consistent hashing internally. So every query that it receives, it is going to figure out the key and hash it onto a node which it belongs to, and then forward the request to that key. Forward the request to that node. Sorry. It is multi-datacenter replication, and it's linear scale. What linear scale means that when you add nodes to the cluster or when you double the cluster, your throughput also doubles accordingly without any effect in latency. So no effect on latency is what is very important, because then there's no point in scaling up the cluster. Right? We have replication. So the replication we have is between data centers is you can tune it to be either no replication or no encryption at all, or you can have encryption between data centers or between racks. The open source version uses gossiping, but internally we do not use gossiping. I'll tell you what we use in the next slides. So let's drill a little more deeper into how the topology looks like. This is very unique to Dynomite. Like the way we deploy is specific because we want the availability zones sync up with the data replica set that we have. So as I said, our typical deployment has like 3 regions and 3 zones in each zone. But in the figure, for simplicity, I'm showing it over here. It's on the left is DC1, which is one data center. On the right is another data center. The first data center has 2 racks in it. So the way data gets replicated is every rack has 1 copy of the data, right? So 1 rack is the entire data set that you have. And that data gets replicated in every rack and every region that you have. So depending on the configuration, you can either have 3 replicas or 2 replicas. So in this case, there are 3 nodes in every rack. And considering that the token distribution is the same, in that way, A1, B1, and C1 would have the same copy of the data. So we have multiple racks for high availability, and each rack contains the entire copy of the data, right? So now let's dig into further as to how the queries get replicated within Dynomite. So in the figure you see, on the top there's Dyno client, but I want to mention that it is not necessary that you should use a Dyno client. Many of our use cases actually use Python Redis client, and We even use Redis CLI extensively to debug issues in Dynomite and all. So the protocol that Dynomite uses on the wire is straight away whatever the data store uses internally. So let's say a Dyno client is sending a request to A1 over here. What A1 does is basically it hashes the key and figures out who is the token owner for that key. And then it forwards it to the local, to the token owner in the local availability zone, and then gets the response and returns it back. So this is for a read. But if it is for a write, along with sending it to the local ASG, it is going to asynchronously replicate to the rest of the availability zones and the racks. It will send only one request to the remote region, and the receiver on the remote region actually fans out the request further to make copies. So every node over here has the complete view of the topology as to how the nodes look like and what is the token distribution. So it is not required that all racks have the same number of nodes, or all data centers have the same number of nodes. You can have like asymmetric deployment. You can save some cost on putting lesser nodes on data center which you are not going to use much, but you just need it for disaster recovery. So that's how write also gets replicated. All that is asynchronous. Now let's dig a little more deeper into tear out a node and see how it looks like, right? So the ecosystem has a client, as you see on the top, which talks to Dynomite node using the Redis on-wire protocol. Dynomite to Dynomite is basically either SSL-based encryption or no encryption at all. Dynomite is essentially a program written in C. It's a proxy layer on that sits that runs alongside Redis on that node, Redis or any data store for that matter. Dynomite-manager is a sidecar, or it's a process that is written in Java, which we use internally for multiple purposes. Primary role of Dynomite-manager is basically to monitor the health of Dynomite and the underlying data store. Along with that, it also does reporting of metrics to the internal Atlas server. I think Atlas is also open sourced. And it also acts as an admin console for performing functions like S3 backups, restores, and node warm-up and stuff like that. Consistency. So this is like a best effort consistency. Since this is an AP system, we cannot really guarantee strong consistency, but this is like a quorum base for applications which require to read the writes that they have just written. They typically use quorum consistency. So DC1 and DC quorum are the two tunable consistency that we use. These terms are basically borrowed from Cassandra, but what they essentially mean that in DC1, you guarantee only the write or read from the local ASG, and in quorum you essentially guarantee writes to quorum number of nodes in the ASG. So if you have 3 racks, you are guaranteed that you are written the data to two racks before you respond. So by that you can say that if there's another read coming in and it is going to do a quorum read, it will essentially see the latest data that has been written. And we do check some calculation on the responses before we return for comparing of quorum responses. Consistency can be configured dynamically for read or write operations separately. So you can either configure read consistency to be quorum or write consistency to be quorum or both, and this you can change it dynamically. The only caveat over here is this is like cluster-wide configuration. You cannot do like per node or per connection. The code has the capability to do it, but we haven't yet implemented it. We haven't gone to that length to do it on a per connection. But if there's a need, it can be like modified it easily. So we did some performance setup of performance comparison of Dynomite. We wanted to basically wanted to see how Dynomite performs under load with different sizes, right? So the exercise was not basically to say that we are this much fast or we can do this much. What we wanted to see was if a client app or someone comes to us and say, hey, we want to create we want a Dynomite cluster of this much SLA. We wanted to create a proper judgment. We wanted to make the right judgment and create a cluster appropriately. So the idea here is to just figure out how Dynomite can perform under load. So what we did was we created different size clusters of 3 nodes, 6 nodes, 12, 24, 48, and so on and so forth. And we wanted to see how it performs. So we use Pappy as an internal load generator tool. It's not open source yet, so it is basically, it creates a cluster of nodes and it throws load on the Dynomite node. So the Pappy is configurable. You can again add drivers for Cassandra. You can add drivers for Elasticsearch or Dynomite, so on and so forth. So we created a cluster which was specific to one region, and it had three availability zones. We deployed it in US East 1. Every zone in our cluster had the same number of nodes. The demo app that we used had performed only basic get and set operations. We did not do hashes or stuff like that because that was not the purpose over here. We didn't want to test the underlying Redis, but we just wanted to see how replication performs and how Dynomite performs. The payload that we used was 1K, and we had like 80% and 20% ratio of reads and writes. So this was what was the throughput performance that we saw. So as you see in the graph, as we doubled the cluster, the throughput actually doubled. And we were able to get more than 1 million client requests with just 24 nodes in the cluster. And this is 24 nodes in the entire region. So it means that 8 nodes per AZ. So this is the latency graph that we observe on that. So on the leftmost is Dynomite average latency. It means that it was only the server side latency that we saw. And on the right is client side median read and write latencies. So we saw that the client read and write were like sub-millisecond. This was probably much better than we expected. This essentially showed that we got what we wanted to achieve out of Dynomite. And these are the 99 latency graph. So we generally in Netflix observe 99 latency graph because some of the services are very sensitive to the latency. And as you see over here, most of the latency is basically taken up by the network. The Dynomite latency, the server-side latency itself is pretty low. For the sake of this session, I've just limited the graphs to just DC1. But we had actually published a post on Netflix Tech Blog back in January, which does a whole extensive test of Redis with pipelining and with quorum. So if you are interested, you can go to the Netflix Tech Blog and have a look. All right. Yanni will now continue on the Dynomite-manager.
So one comment about the latencies, I think more than 50% of those latencies were mostly socket latencies rather than Dynomite and Redis latencies. So the processes themselves seem to be pretty fast in any case. Based on experience we have for Cassandra for operating the last 6 years, we have a sidecar. So we took some of the baseline code that we had on a product called Priam, and we adapted that for Dynomite specifically on how we can manage Dynomite in a cluster in production. So Dynomite-manager itself, it does token management for multi-region deployments. So it creates the tokens based on some in-local algorithm, and then uploads those tokens to a Cassandra cluster, so we can query at any point of time where we want. When a node goes down, it can query the database, comes back, and takes the token from that data store. We created Dynomite-manager in order to deploy that in AWS. So it has a lot of APIs that are specific to AWS. The way we develop Dynomite-manager is through Java interfaces. So if you do want to deploy Dynomite-manager in other environments like Google Cloud or Azure or other, then it's easy just to implement those specific APIs. Dynomite-manager does an automatic security group update, which means that it opens the ports in order for the nodes to connect and discuss them, and talk between themselves. It does monitor Dynomite and the underlying storage engine, which in this case is Redis. It actually does two things to monitor. First, it checks if the process is alive, and secondly, it does perform a ping on Redis to see if the Redis itself can accept data. If it does accept data, it means that it's alive and it can accept client requests. And It does the same thing for Dynomite as well. It does perform a ping on Dynomite using the Redis CLI, the Redis ping, and it also checks if Dynomite data is live. If all the cases for the health check are fine, it reports back to Discovery and says, Discovery, this node is healthy and it's operatable. If something happens and one of the health check fails, then it reports back to Discovery, this is unhealthy. We take it out of Discovery, and then Dyno automatically fails over to another node, so we don't lose any data in that case. Dynomite-manager performs a node called bootstrap, which means that the node goes down, it comes back, we don't lose data, we just use Redis underlying replication to stream the data from another node. I'm going to show you how this happens. And of course, for disaster recovery, we do implement S3 backups, and it's done automatically on a scheduling basis through Dynomite-manager. Dynomite-manager is fairly easy to communicate with. We use just S3 REST calls to it, and you can perform many actions through that. So the way that the warm-up functionality works is Dynomite-manager checks which other node in another availability zone has the same token. And once it finds that node, then it uses that node to stream the data using the Redis master-slave replication in the background. So during the time that we warm up the node, we still keep it out of production until once it's warmed up, then we bring it back to discovery. So effectively, what it does, in order to determine if that node is ready to accept data, is in sync, effectively it checks the peer syncing on the master node, checking the Redis info information. Once the two nodes are in sync, then Dynomite releases and say this node has all the data, it is all the data have been fully replicated. Now we convert it from slave to master and we bring it back to production. And of course, in the end, we check if everything is healthy in order to make sure that there is no other problem happening. So this is an example here that the node gets terminated in AWS. And then as you can see, there is, that doesn't work. So there is another node in another availability zone that has exactly the same token. So the node comes back through auto-scaling activities by AWS. Once that is up, Dynomite-manager detects that there is another node that has exactly the same token, which means effectively inside the token ring, it has exactly the same data. And then it sets that node as a master. It sets itself as a slave. Once this is done, it uses diskless master-slave replication from Redis in order to stream the data to the slave. Once the data is in sync, then we release that back to production, and therefore Discovery knows about it. We also have S3 backups. So as I said before, we have two use cases for Dynomite and Redis. One is as a cache, and one is as a data store. And for those people that use Dynomite as a data store, we definitely don't want to lose their data. In order to do that, some customers have asked that they want to back up their data to S3. There's another use case about data corruption. Sometimes software engineers may make mistakes. They may change some data, and therefore they want to roll back to the data in a previous day. And there's another third case, which I didn't include, is refresh and restores. Sometimes we want to do testing, like A/B testing. So we want to move production data to test. So this can happen also with S3 backups and restores with Dynomite. So effectively, the way we do that is on a scheduling basis. So Dynomite-manager spawns a thread on a scheduling basis, and then backs the data, dumps the data to the drive. And then it uses S3 API to send the data to S3, to an S3 bucket. The data, as we said, most of our production instances are R3 2x large, which means that we have 64 gigs in a per node basis. So we don't use incrementals because our file sizes are not that big to actually use incrementals. We do have a couple of nodes that are used R3 8x large, which are 256 gigs. But right now, this person only uses that Dynomite cluster as a cache. So long story short, if you have data that have very short TTL, then there is no reason to do S3 backups, obviously. And we do perform backups on a daily basis, on a specific time while everybody's in the office, of course, in case there are high latencies. But as of now, everything looks good. So the way we do backups is, again, either through a lightweight thread that spawns on a specific time during the day, or through a REST call. Let's say some customer comes to us and says, I want to persist my data right now because I'm going to start a test in about 15 minutes. Then we tell him, OK, wait, we're going to persist your data, and you can start your test in case something happens. We do BG write AOF and BG save in the background. So we used the forking mechanism that Redis uses for that perspective. We check the size of the file that we have persisted, and if the size is above 0 and everything is fine, then we send this to S3. The way we store the data in S3 in our buckets is effectively we have this is the backup, this is the region, this is the cluster name, this is the token, and this is the date. So every time somebody asks, I want to restore my data for a specific date, we have all the information. And we exactly through the token know exactly where the data will come back. Restores can either be performed. So if a customer says, I want to do, let's say, refresh and restores right now, I want to move some data from production to test, and we can do that. Effectively, once we do that in test, during the start of Dynomite-manager, we can enable through a fast property, which is a configuration, to do the restores. Or otherwise, we can do that through a REST call. In that case, we stop Dynomite process. The reason we stop Dynomite process is because we want Dynomite-manager to inform discovery that this node is getting out of discovery. Once the node gets out of discovery, then automatically the client will fail over to another node, so the customer will not lose any data or will not have any downtime. And after we do that, we stop Redis. So, of course, we store the data on a specific date. We start Redis. The data are loaded automatically by Redis, and then we start Dynomite, and we bring those nodes back to production. In order to fully take advantage of the features of Dynomite, we have created the Dyno client, which is effectively a wrapper around Redis. So, as Saleh said, you can use any Redis client to talk to Dynomite. The APIs that we support are on GitHub, but we support the majority of them. So Dyno client uses connection pooling. It does load balancing. So if you do use Dyno client, there is no coordinator node on Dynomite because Dyno client is token aware. So automatically it uses the same hash algorithm as Dynomite, so it will automatically send the data to the proper node directly. It does do effective failover, which means that once it detects that the node is out of discovery, there is some issue, it automatically fails over. So that request is not lost. There's one try, second try, third try, it tries to fail over. The way we have Dyno to fail over, once it fails over, it sprays the request to the other nodes that has failed over, and we do that again for extra load balancing. You can do pipelining, scattered gather, and Dyno client is also, if you use Netflix OSS ecosystem, it is also integrated with Insights, which is Atlas, the metrics we use inside Netflix to observe what's going on. So this is how Dyno client employs token-aware load balancing. Effectively, the way the tokens are distributed inside Dynomite follows the same principles as Cassandra, but with the difference that every node has a single specific token range. So effectively, once data come to Dynomite and they are hashed, if they belong to a specific token range that this node is handling, then the data will store to that node. And since Dyno is token aware, it will be node to which exactly node it has to go to store the data. So therefore, there is no need for a coordinator node. So again, there might be cases that one Dynomite/Redis node is down, and we need to fail over, and we don't want any downtime. In that case, we just retry in a remote track in order for us to get the data. So some of the features we plan to implement in the future, one thing is a multi-threaded support for Dynomite. Of course, the latencies are low, but we think there might be some improvement on having separate threads for cross-region or a cross-track replication. We're almost done with the first version of data reconciliation and repair. So, for example, if some data cannot be sent to another AZ and we lose the data, we have a reconciliation engine that we plan to deploy in production in a month or so for that. We're looking in different persistent data stores as well. We are looking at ARDB, LMDB, which are effectively, there are some open source projects that do use the Redis API to use them. So we can use that, for example, as an L1 Redis L2 cache as a persistent data store, or we can even use them as another solution for people that actually need persistence and not in-memory data. We're working towards a Dynomite Spark connector, and there was a very nice talk earlier today about Redis Spark connector as well, and also implementing asynchronous calls from the Dyno client. And of course, this is an open source project, so if you do have any recommendation about features you would like to see, please open an issue or let us know, and we'll love to work with you in case we can do that. Again, these are the links where you can find information about Dynomite and Dyno. Dynomite-manager, which is the sidecar, has not yet been open sourced. We plan to do that in about a month as well. We're in the final steps. So again, if you do have any questions, let us know. These are our emails, but also you can use GitHub to post any issues that you have or questions.
So just to mention, we also have a Netflix OSS meetup on 1st of June in Los Gatos. So if you are interested, you can come over and we can further discuss about Dynomite and all. And we also have open issues on Dynomite GitHub. So if you think this project is interesting and you want to contribute, we have issues tagged as need help, and you can take a look and feel free to pitch in if you want. Right? Any questions?
So are you talking about token collision in that case? The two nodes have the same token, the one didn't get out of discovery. We haven't faced that issue right now in production. We have faced that with Cassandra a couple of times, but we haven't seen that issue with Dynomite right now. One of the differences, I said, that Cassandra uses a token range across nodes, and we use a token range inside a specific node. So once that node gets out of discovery, that node is effectively invalidated for that time, right? So in any case, there cannot be two nodes at the same time in production that have the same token in one availability zone.
That's right. I'm only talking about zombie records, the data that you mentioned.
So zombie records for nodes, you mean?
Yeah.
So the discovery service is going to say that this node is down, right? And Dynomite-manager actually informs Dynomite that, hey, this node is down. And that's how Dynomite actually gets its updated topology. And later on, when Dynomite-manager actually, when the other node comes up, it is going to actually see which token it is replacing. And it is going to say, okay, I'm the new token now. And that's how the Dynomite discovery service actually, and we use the same technique for Cassandra as well, that we use that this node has replaced an older node, and this is the new node that you should communicate to.
Do you use timestamp to identify that address?
No, we don't.
Right.
Which host OSs do you use in production? Is it all Ubuntu or CentOS?
Trusty, Ubuntu, right now. But there are people, I think, online on GitHub that are using CentOS. There was an Ethingas issue 2 days ago, and there was a fix today for that as well.
How do you insert new nodes in the cluster, and how do you specify it?
How do you add new nodes? So the question is, how do you add new nodes to the cluster? So in the long term, we want to see that this is going to scale up linearly, like you can just randomly add nodes and it will auto reshard and all. But that is something that we don't have today. The way we do it is either we do dual writes and create a new cluster temporarily, because many of our use cases have TTL based data, so we use dual writes and all for such features. And if there is a need that you need more capacity, there are two options, either like I said, the dual writes, or you can push a new AMI with a larger instance, and then you can do a rolling termination of one node at a time.
Right. So because we use a highly available system and not a master slave, for us we can terminate any node in production and there is no problem because the data will be warmed up automatically. Right. So there's no data loss in that case. So for us, what we can do is we can push a new AMI with a better instance type if we want to vertically scale, if it's an median case, but it's more like a long-term case, so let's set it right. We can just double the cluster and do dual writes on the Dyno side as a pattern, and therefore bring that TTL the data out in the older cluster.
Yeah, you really need to see whether you want to add this mechanism of auto resharding, or whether you want to just temporarily create a double cluster and be done with it, right?
So there are a couple of vendors that will be actually in the meetup that will talk about how they operate Dynomite in production. But there is an open. I think two folks have created already an open source version of what we call Dynomite-manager, we internally call Florida, inside our GitHub repository. So it does have some functionalities for token management. It doesn't have the full-blown functionalities for warm-up and backups. But Dynomite-manager is almost ready to get out as an open source project.
That's asynchronous replication. and Dynomite takes care of replicating data. So what is your question around it? Yeah, it is asynchronous. So yeah, it is async. So if it is a quorum kind of a read or write, then the client request is going to essentially wait for the Dynomite coordinator is actually wait for those responses for that request before it responds back to client. So it really depends on the configuration of the consistency, but by default for a DC one, it is always going to be asynchronous replication. Yes. So there are chances that since it is asynchronous replication, the coordinator node might go down. It might acknowledge the write to the client and say that okay, I'm done, and then the write is never replicated. So that in that case, the write is lost. So for such kind of a use cases, we recommend customers to use TUNIP the DC quorum consistency so that they know that at least 2 of the nodes have written the write before they go.
Yes, we have done. I think we did a month ago or so. We tried LMDB and RDB, and it was like plug and play because they use the Redis API.
So one instance which is LMDB and one instance which is Redis.
No, we used, in that case, what we wanted was, so this was more like for us to do an exercise, how difficult it is, number one, and how fast it is, right? So for us was just put an LMDB in a cluster and see how fast it is than running 2 of them together. So it, as I said, it typically tries twice. If it doesn't find the data, it's going to fail over to another node inside the same region. But we keep 9 copies of the data, right? That's the idea. It's 3 replicas per availability zone. So we keep 9 copies to be safe that data will not be lost.
So it depends on the deployment.
Yeah.
A typical Dynomite deployment, some of the Dynomite deployments in Netflix are 3 regions, 3 racks. And recently we have also started deploying RF2, which means that you have only 2 replicas within a region. Some of the deployment have just 1 region, so it really depends on the deployment, but essentially it boils down to you have 1 replica per availability zone. No, that's not a typical deployment. So the typical deployment is 2 or 3 racks in the local region, and if the app is multi-data center, like you can expect reads and writes on other region, then you have the apps deployed on multiple regions.
So I'll ask the first question. If A1 goes down, it comes back, it gets warmed up, it gets back to discovery with the same nodes. Once it gets back to discovery, Dyno detects that and it will move back to sending the traffic to that node. So why, if it falls back to A1, right, it will start failing again? Because we just moved it back. We did the health check. Dynomite-manager does a health check. It makes sure that it is running. If it's not running, it will not bring it back to discovery. If it does bring back to discovery, Dyno will continue getting the data from the remote racks. Yes. So you inject the dependency of your discovery service in Dyno. So that's how you effectively Dyno.
And you will keep connections open to all the nodes.
Right.
Yes, it has connection pooling and pre-connects and all.
But
And
the maximum connections that a Dynomite node can accept is around, when we tested, around the 80,000. So keeping the connections on, that doesn't create a problem for us.
What do you use for polling consensus? Do you use patches or?
No, this is not that strong consistency. This is a best effort consistency. We make sure that we get a positive response from at least 2 nodes out of 3 before we return back that okay, we are good. Otherwise, if we don't get, you send that okay, we failed. And then the next quorum read would essentially mean that you will get the right read. Make sense?
Does it make sense to have deployments with only 1 physical box in each rack? So you only have 1 server per rack?
Yeah, we have deployments. Actually, it depends on what is the customer requirements. We have some clusters which has just one node per rack. Yeah, we can still fail over and out. So essentially, it means that 1 Redis node active throughout.
So we'll accept 1 to 2 more questions because we have to wrap up. So we have buckets in all regions, and all nodes in all regions do a background AOF or a background save, and then we send to the corresponding buckets using the token. So we have all the data across whole cluster.
Like it's like taking a global snapshot.
No,
Right.
so that is a global snapshot, but it is not a point-in-time snapshot, right? So it is not a point. There are this is a difficult problem to have a point-in snapshot in a distributed manner, and there are actually full-blown companies around it. So no.
So in Netflix, our majority of clusters are Cassandra, but we ended up having this problem that Cassandra was not fast enough, right? And there was a lot of community was building using Redis, right? So they wanted a short ETL of data or data storage at an extremely fast, or low latency. Therefore, this is what they need to do. So we are trying to cover a use case for that. So think about Cassandra sitting here, Dynomite sitting here. So high persistence, low latency, high persistence, okay latency, high throughput, low latency, persistence not on a per request basis, right?
Maybe for the use cases that are applying at the intersection of the two, what's for you the really factor that moves the decision from one to the other?
So if a customer has a lot of requests, right, per second, they can't do that with Cassandra. Or we even have a customer that is behind you that wants to implement some queuing on Cassandra, and he couldn't do that. So he's creating a layer above Dynomite for queues as well. So there are different use cases, right? Every customer is different. So I think we're almost done.
Yeah.
If you do have questions, we'll be sitting here.
Outside.
Or outside, yeah. Sorry.
Thank you.